Hi students, it's Dr. Marks, and we are continuing in our discussion of probability. But unlike what we did in the basic lecture, we're going to do some more advanced topics and deal with issues when we have events that are related. Now, this does mean more equations, but I'm going to do my best to help you see that all we're doing is slightly altering some of the equations that we've already dealt with. I'm going to try to make sure these are as connected as possible. So let's get started. Now, in the previous lecture, as I just said, we covered some basic probabilities, but we also had some simplifying assumptions. So if you remember, we assumed things like we have independent events. We assumed disjoint events. For example, if a roulette ball lands on red, then we know it can't have landed on black. So we have these disjointness that makes things a little bit easier. But here we're going to add on to our knowledge, and as I just said, it does mean more equations. But I'm going to do my best, as you'll see in this lecture, to show you that we don't really have as many equations as it's going to look like we do, because some of them are just small alterations of other equations, where we either have to subtract something or add something small. So I'm going to do my best to try to show you those patterns, to keep it as simple as possible. Now, one thing that we need to look at is what we call the additive rule for non-disjoint events. So what happens when A and B overlap? Because we've been assuming that we have disjoint events. For example, the probability of red or even in a roulette wheel. Well, we can't apply the idea of disjoint events because red and even overlap. Well, that's going to require a new equation. And what if we want to look at a conditional probability? And that's the idea where, for example, in roulette, the probability of landing on even, given the ball's red, right? One is conditional on the other. So what's the chance that I land on even, given that I know I'm landing on red? So I have to take those conditions into account. Then we have to introduce a multiplication rule when we don't have independent events. For example, what's the probability of drawing a heart from a deck of cards and then another heart? Do we agree that the probability of drawing the second heart depends on the fact that I've already drawn a heart? It changes the probability. And so we have a joint probability in that sense where those events are dependent on each other. Now, I don't expect you to understand everything I just said. We're going to go through each one of these very carefully. But before we do that, let's just go back to our notation and review it because it's been a little while. So we've talked about a strict subset. We've talked about a subset. We've talked about the U symbol, which we're going to see again in this lecture, meaning union of. But that's kind of confusing because we think of union like I have a marriage with my husband. We are a union. It's an and, but no, it's not. It's or. So the union of, that U sign means event A or B, whereas the upside down U means the intersection of event A and event B happening together. So those two things cause a lot of confusion for students. So I just need you to get that down now, that union, the U means or, the upside down U means and. Then we have our 0 with the slash through. We said that's our empty set, our null set, meaning it contains no values. And we've got A with the C superscript, meaning complement of. It means not A. So what's the probability of A not happening? All right, let's move on. So we're going to jump right into it, gang, and start adding onto our equations. Now, if you remember, in our first lecture, we had equations 1, 2, and 3. We looked at a simple probability, we looked at complements, and we looked at the additive rule when we had disjoint events. So all we're doing here is jumping into number 4, where we're saying, okay, we need an additive rule when things are not disjoint. All right. So we're asking here in this case, what's the probability of the union of A and B? In other words, that A or B happens, and we've got our notation, right? So the probability that A or B happens. Now, if you remember in the first lecture, we expressed it like this, right? This was rule number 3, or rule number 2, I can't remember, but it was our additive rule for disjoint events. We said all we need to do is add probability of A and probability of B. But here's the deal, gang. This was under the assumption of disjoint events. In other words, it was under the assumption that we have no overlap in the outcomes. So red, black, they have no overlap. They are disjoint. So what this means is that part of our equation dropped out when we had the assumption of disjoint events. So back to that red equation in the 5th line. That's the equation we have been using in our lecture on basic probability, but it's not going to work here when we have when we have non-disjoint events. So here's the thing, something dropped out of that equation. What we have to do now is put it back. So I hope I'm being clear. The equation we've been using for additive rules, something fell out because we had disjoint events. Now we're going to put it back. All right, so what am I talking about? I know you're like, Dr. March, what are you talking about? All right, here we go. This will make it clearer. This is actually the equation for the additive rule. But as I said, something dropped out when we looked at our previous application because we had events that were disjoint. And it's that part right there, right? That last part. We didn't have that before. So this is the intersection of A and B. We have to subtract that off. Now, look at the yellow note. It says A and B are disjoint events. What would this term be equal to? So in our assumption from before, when we assumed we had disjoint events, what do I know about that term, folks? Remember, we're capturing the intersection, the overlap. Well, let's think about it. Do you agree that if A and B are disjoint events, there'd be no overlap? So that part would have been an empty set or a null set. That's why it fell out in our previous equation. But now, gang, we're going under the assumption of not disjoint events. So if they're not disjoint events, then I do have overlap, and this is no longer the empty set. So as the note in yellow says, this part in blue, it's not the empty set anymore. It's going to have something in it. This is the part we need to put back because now we have not disjoint events. All right, I realize that not everyone followed that, so let me show this to you another way. Because for some of you, I know you're very visual, equations aren't quite for you. This is going to help you out. So I've got 2 events here, and A and B, and do you agree they are not disjoint? How do I know they are not disjoint? Because they overlap. There are elements in common, right? So I know the assumption of disjoint events, that's not going to apply here. So the problem here is if I just add probability A and probability B, do you agree I'm going to double count something? So look at that note in blue. That area where you see my red arrow, that's being double counted in our equation. So if all I do is add probability A plus probability B, I'm going to double count that twice. So what I'm going to do is subtract it once. So guys, look at that red equation at the bottom. We've got probability A plus probability B minus the overlap. Now remember, I didn't need that before because with disjoint events, there was no overlap. So gang, is this really a new equation, this equation number 4 for the additive rule for not disjoint events? No. All it is the same equation we used before, but putting something back that's now relevant. So let's do an example. Let's say that we have cities that are competing to host a future Olympics Games. And the committee making decisions is going to narrow down to 5 finalists. Okay, so we have bunch of cities competing to host the Olympic Games in the future, and the Olympic Committee needs to narrow down to 5 finalists. That's their plan. And there's a 20% that Paris will be a finalist, and there's a 35% chance that Rome will be a finalist, and there's an 8% chance that both cities will make it to the finalist list. So, do you agree here that we have an event A, Paris is a finalist, we have an event B, Rome is a finalist, and then we have a probability of 8% that both A and B are true. So we want to know, what is the probability that Paris or Rome will be a finalist? In other words, the probability of Paris union Rome. All right? But that means or. So let's work this problem. First, do we agree that these events are not disjoint, right? Because these cities are in competition with each other. If one gets selected, it reduces the probability that the other gets selected, right? So when Paris gets selected, it's going to impact the probability that Rome is selected. So these are not disjoint events. Hopefully that's clear. Now, all we have to do is use our equation. But I want to point out one thing to you. There's an 8% chance that both cities will make the finalist list. Why am I giving you that information? What does that have to do with this calculation? So I've got event A with a probability of 20%, event B with a probability of 35%. But we have this overlap because they might both be on the finalist list because there's going to be more than one finalist, right? So I've given you our intersection. So I've made this super easy. So now we calculate. So let's just start by looking at the equation. We take the probability of A plus the probability of B minus the intersection of, right? Minus the overlap. So the probability of A is 0.2. Paris will be a finalist. The probability of B, 0.35. Rome will be a finalist. Subtracting off the intersection, 0.08. So we have a probability of 0.47 that Paris or Rome will be on the finalist list. But again, because we have non-disjoint events, we had to remove the overlap. That's the only thing we're doing here new, gang. So you already understand the additive rule. All we're doing here is saying, oh, okay, non-disjoint events, there's some overlap. I have to remove it to avoid that double counting problem. Let's do another example. So example number 2, you're removing a card from a deck. And we want to know, what is the probability that it's an ace or a spade? An ace or a spade. Do we agree that these events are not disjoint, right? Do they have overlap? Do the aces and the spades have overlap? Of course they do. What is the overlap? How many cards overlap between ace and spades? Well, the ace of spades, right? That's the overlap. There's a card that overlaps, and that's the ace of spades. So, if I want to calculate the probability that the card is an ace or a spade, look at my equation. I have to calculate the probability of getting an ace plus the probability of getting a spade, and then subtracting out the overlap so I don't count it twice, which is the probability of an ace of spades. So the probability of an ace, there are 4 aces in a deck of 52 cards. So the probability of getting an ace is 0.0769. And the probability of getting spades, well, there are 13 spades out of 52 in a deck. because remember there's 4 suits, so it's going to be 1/4 of the deck, equals 0.25. So 1/4 of the deck is spades. So if I just add these together, probability of ace and probability of spades, that's going to be a little off because both of those calculations include the ace of spades. Everyone agree? The ace of spades appears in the 0.0769 and the ace of spades appears in the 0.25. So now we have to remove the probability of ace intersect spade, the overlap, which is going to be the card ace of spades, and there's only one of those, so that's why I have 1 divided by 52. The probability of the ace of spades is 0.0192. So now I have all of the components that I need, and I'm just going to plug them in. Probability of ace, 0.0769, plus the probability of spade, 0.25, subtracting off the overlap, 0.0192, which gives me 0.308. So the probability of getting an ace or a spade is 0.308. So again, make sure you're clear. The only thing that we've done here, gang, is removed the overlap with the ace of spades. Otherwise, it's the same equation that we worked with in the first lecture. Let's look at one more example. Let's say we're talking about cars sold in the United States. Cars in the United States can be categorized as either cars or light trucks. So you might be thinking, well, what about those SUVs? Well, they would be light trucks. So cars or light trucks. But we can also divide the data on the fact that some of them are domestic and some of them are imports. So we've got cars and light trucks, we've got domestics, and we've got imports. So let's say we have the data that says 68% of new vehicles sold were domestic. Vehicles, they could be cars, they could be light trucks, but 68% of all vehicles sold are domestic, and 54% were light trucks. Doesn't matter. They could be domestic or imports, but 54% were simply light trucks. But 47% were domestic light trucks. So specifically light trucks that were made in the United States. So take a look at that data for just a second. So we've got 68% of our new vehicles are domestic. We know that 54% of vehicles sold were light trucks. They could be domestic, they could be imports, and 47% were domestic light trucks. So very specific information. So we want to know what's the probability that a car chosen at random is domestic or a light truck. Okay, so we're using the same equation that we've been working with. Do we agree there's some overlap between domestic and all light trucks? So these are not disjoint, right? Because we have two events, domestic or light truck. But we have some outcomes in common, right? There's going to be some overlap. So we need to make sure that we remove that overlap in our calculation. Well, what is the overlap between domestic and light trucks? Well, our light trucks are those SUVs and minivans, some of which are domestic. Ford Windstar, GMC Terrain, they are domestic light trucks. So we need to remove the overlap. So back to our data. We have 68% of new vehicles were domestic, 54% were light trucks, and 47% were specifically domestic light trucks. What is that number that I've got in red telling us 47%? Well, that's our intersection between our event A, domestic, and B, light trucks. That is the portion of outcomes that falls into both categories. So I have to remove that. So we want to find the probability of domestic or light truck. So now we know what to do. We are going to take the probability of domestic plus the probability of light truck and then subtract the overlap, which is the probability of a domestic light truck, right? The overlap between domestic and light truck. So to do this, I need to take probability of domestic, which is 0.68, plus the probability of light trucks, 0.54, and subtract the probability of the overlap, which was double counted, the domestic light trucks, 0.47, and that is going to give me 0.75. So if we take any random draw from this sample, it's going to be a probability of 0.75 that we end up with a domestic or a light truck automobile. Now, before we move on, let's understand the difference between additive rules and what we're going to move on to next, which is multiplicative rules. So in the additive rule, we just did a number of examples of that. We wanted to know what's the probability of getting an ace or a spade. And we calculated the probability of 0.308. And we used the additive rule. But we're going to talk about the multiplicative rule, which is going to be for a different context. So the additive rule, we want to know what's the probability of A or B. But that's not the same as what we see on the right. That's looking at the probability of an ace intersection spade. In other words, the probability that a card is an ace and a spade. Now before we go on the left we're saying ace or spade. On the right we're saying ace and spade. And we're going to get a different probability because there are a number of cards that could be an ace or a spade. But look on the right. If I want to know the intersection, ace and spade, do we agree there's only one card that meets this? And that's the ace of spades. So 1 divided by 52, because only one card will have both of those qualities, 0.0192 is our probability. We need what we call the multiplicative rule for this. But the example I just gave you is for dependent events, and we'll come back to that. But I just want you to understand the difference between or and and. That's what I want you to understand at the moment. I want you to understand that or requires the additive rule, but when we talk about and, we have to look at a multiplicative rule, which means more equations. All right, so let's move to our multiplication rule for probability. So we just looked at the probability that A or B happened, right? We looked at a randomly selected car and we wanted to know the probability that it was domestic or a light truck. So what did we do to make that calculation? We used that additive probability, but that was for or. What if instead we want to look at the probability that A and B happened? Well, now we have to look at the multiplication rule. So in this case, we'd be saying we want the probability that a randomly selected car is a domestic light truck. It is domestic and light truck. Before we were looking at or. Now we're looking at and. So what we're doing here is looking at what we call the joint probability. And to find a joint probability, we need the multiplication rule. But in addition to the multiplication rule, we need to know if we have independent events or not. So just like before, we had two additive rules. Was it disjoint events or non-disjoint? Well, same kind of thing here. So hopefully you're thinking, okay, that must mean we're going to have two multiplication rules, and that's exactly it. We're going to end up with two additive rules, we've already got those, and we're going to have two multiplication rules. So when using the multiplicative rule or the multiplication rule, as I said a minute ago, we're calculating a joint probability. So what do I mean by joint probability? Well, a joint probability is the probability that multiple events happen. It's the probability of A and B. So before we looked at or, now we're looking at and. So or we use the additive rule and we use the multiplication rule. Now the equation that we use for multiplication depends on if A and B are independent or not independent of each other. In other words, does knowing A occurred change the probability of B occurring? If the answer is yes, then they are not independent. So when do we have independence? Let's get our brain around this because this is what we're going to work with first, this assumption. Well, to have independence, it might require separation in time or in space. For example, let's say we're going to play 3 rounds of roulette. What happens in the first round, do we agree, does not impact the second round, right? I spin that roulette wheel first, I have an outcome, and that has no bearing on what happens the second time I spin. And that has no bearing on the third time I spin because these are events that are separated in time, one after the other. They are clearly independent. We might have other examples in the workplace, for example. Maybe there's a weekly drawing for a free lunch. Are these independent events? Well, the answer is it depends. It depends on if I replace the name each week, right? So if you can win over and over again, what that means is we're sticking your name back in the hat. In other words, we're drawing with replacement. That would be the statistical term. We're drawing with replacement. So do you agree if we're drawing with replacement? We call a name, oh, Bob gets a free lunch. We're putting Bob's name back in the hat. Do you agree these are independent events? They are independent over time, right? Probability of pulling Bob's name in the first round doesn't affect the probability of getting Bob's name in the second round. And the fact that Bob won the first round doesn't change the probability that we draw Susan's name. It's all independent. So by the same logic, drawing a male this week tells us nothing about if we're going to end up with a male or a female being drawn next week. The probabilities are not changing, again, because we're drawing with replacement. So when we draw out of a hat from statistics, we need to know, hey, are we drawing with replacement or not drawing with replacement? Because that tells us if we have independence or not. So I need to always be clear. Are we drawing with replacement or not, if it's not obvious? Now, if you can only win one time, so we pull Bob's name out, he wins his free lunch, he cannot be entered into this drawing again. Do you agree then these would not be independent events? All of a sudden, we have dependence. We do not have independence. And we would call this drawing without replacement. So the statistical idea is that we're drawing without replacement. So drawing a male this week changes the probability for next week, assuming that we don't have anyone quit their job or, join the firm. So we're just keeping the names in the hat the same. But I pull Bob's name out, okay, that changes the probability for everybody next week. There's one less name. And if I wanted to know, okay, if I have 50-50 male females and I pull out a male, do we agree that changes the probability of getting a female next week? So I could ask you lots of questions under the assumption that we're drawing without replacement. But we understand when we are drawing without replacement, we have dependence. We do not have independence. All right, so now let's move on and actually look at the equation the multiplication rule. We're going to call this equation number 5. So remember, we've already looked at our basic probability rule, we've looked at our complements, we've looked at our additive rule for disjoint events. We had our additive rule for non-disjoint events. That was number 4. Number 5, our multiplication rule for independent events. Can you guess what number 6 or 7 is going to be? One of them has to be multiplication rule for dependent events, but we're coming back to that. So right now, I've underlined independent events. So let's keep it simple. For independent events, then we need to use what I'm calling this multiplication rule for independent events. And it's very simple. It's simply the probability of A intersection B. So remember, how do I say that in non-stat language? It would be the probability of A and B. So remember, multiplication rule is for and. That upside down U means intersection, which means and. And that's simply going to be the probability of A multiplied by the probability of B. And guys, if I have 3 events, 4 events, it's just going to be them all multiplied together. So the probability of A and B happening together is simply the product of their individual probabilities. If I have events A, B, and C, same thing. It's the product of their individual probabilities. And again, I'm going to say this over and over again, we're still assuming independent events, and that's important because there will be a multiplication rule for dependent events. So again, we're saying something like we get heads on the first coin toss and heads on the second coin toss. And we want to know the probability of getting heads and heads. Do we agree? These are independent events. Getting heads on the first coin toss has no influence on our second coin toss. So remember, gang, and I'll say this over and over again, what we're calculating here is a joint probability. The probability that A and B happen. We call that a joint probability. All right, so let's do this example. We want heads and then heads in our coin toss, under the assumption that these events are independent, which would be the correct assumption. So what is the probability of heads intersection heads, which means heads and heads, keeping in mind that what we're calculating is a joint probability? Well, I need to use the multiplication rule for independent events. I just gave it to you. So I just take the probability of heads in round 1 and multiply it by the probability of heads in round 2. Remember, the multiplication rule, why do you think we call it the multiplication rule? Because we're just multiplying together the probabilities to get the joint probability. Well, what is the probability of getting heads? If we have a coin toss, right, on a fair coin, it's going to be half chance of heads and half chance of tails. So probability of heads is 0.5. 0.5 multiplied by 0.5 for round 1 and round 2 gives me 0.25. I have a 0.25 or 1 in 4 chance of landing on heads 2 times in a row. And I'm going to say it again. Remember, this equation that we're working with is a little bit simpler because we have independent events. And we want to remember we have to have a version of this rule when we have dependent events, but we'll come back to that. Let's do another example on our roulette wheel. So you've got your diagram there on the right so you can remember what it looks like. And we want to know what's the probability of red on our first spin and even on our second spin. And, right, the probability of red and even together in 2 spins. Now, these are independent events. Make sure you're clear. I'm not asking what's the probability of getting a red even number. I'm saying the probability of red and then even. 2 joint events. 1 event and 2. The probability of looking at this jointly. We agree that these are independent events, right? So what we said is we're calculating a joint probability. Writing it in statistics notation, what's the probability of red, intersection, even? The probability of red and then even. So we're going to calculate that as the probability of red multiplied by the probability of even. So I need to look at those two individual probabilities. Well, if I want to calculate the probability of red, how would I do that? Well, I know there are 18 red spaces out of a sample space of 38, right? There's 18 red outcomes out of 38. And for even, it turns out we have 18 even outcomes out of a sample space of 38. So the probability of red is going to be 18 out of 38. The probability of even is going to be 18 out of 38. I multiply those together, and it gives me 0.736 multiplied by 0.4736, which gives me a probability of 0.224. So the probability of getting red on the first spin and then even on the second spin, again, I'm not asking a red even on one spin, I'm saying red and then in another event even. That's a joint probability, in this case 0.224. Now, we're done with multiplicative, but only for the case of independent events. As I said, we need to look at multiplicative when we have dependent events, and we're going to come back to that. But we have to look at number 6 first, conditional probability. And the reason we have to look at this first is that to calculate the probability using the multiplicative rule for dependent events, it involves a conditional probability. So I can't just jump right there without first teaching you conditional probability. So let's let that be our equation number 6. So we're going to look at conditional probability. A conditional probability is the probability of event A given that event B has happened. The probability of event A given that B has happened. Why do we call this conditional probability? Because basically what we're doing is we're setting a condition. Given B has happened, that's our condition. So here's an example. Let's say that we roll an odd in roulette given that the ball lands on red. So I'm not saying first I roll odd and then I get red. I'm saying what's the probability that we would get our ball landing on odd if it was given that it landed on a red space? So what we're saying is, hey, we know it landed on red, or let's assume, or let's imply the condition that it landed on red. So given this, that it landed on red, what is the probability of odd? So my suggestion is that when you're thinking through these, that you start with the given. There will be some problems that I give you and some examples we look at where starting with the given is really going to help you see your way to these problems. All right. Now, I want to be clear. When we looked at the multiplicative rule, we were calculating a joint probability. But this is not a joint probability. This is a conditional probability. So we have to make sure we understand joint probability versus conditional probability, and that can be very confusing. So let's just take 1 second and look at them side by side to make sure we're clear. When we looked at a joint probability, and remember we did that using that multiplication rule. When we looked at joint probability using that multiplication rule, we were asking the question, what's the probability of B and A? In other words, the probability of red and even. So we're going to roll our roulette wheel once. We're going to spin it once. What's the probability of meeting both of these conditions together, red and even? A conditional probability is different. We're asking about the probability of B given event A. So what's the probability of red given that we land on an even number? What's the probability of red given that we land on an even number? And those clearly do not have to be the same. Hopefully I didn't pick an example where they are the same, but they don't have to be the same, right? Now, to calculate a conditional probability, we need this equation right here. And this looks a little messy, right? But I promise you, we understand all these components. So let's just look at the first part, the probability of B given A. That bar, that's probability of B given A. So the thing behind the bar is given. The probability of B given A. Now, the numerator, we've seen that before. Remember, that numerator is the intersection of A and B, right? The intersection was that joint probability. How did we calculate the intersection? Remember, that was the AND equation, A and B. Well, that was rule number 5, that multiplication rule, right? So we've seen that before. Of course, we've only done it for independent events at this point. And we understand the denominator, probability of A, right? So that denominator is easy. It's just the probability of A. That's the thing that's given, right? So we're saying, hey, what's the chance of B given the probability of A? So this equation looks a little messy, but there's nothing new in it. It's the probability of B given A, so we need to make sure we understand how to read that. The numerator is the joint probability from equation 5 if it's independent events, and the denominator is the probability of A. So example 1. It's 80% likely that your CEO is going on vacation the first week of January, right? So we're all going to be like, woohoo, time to play. So 80% likely your CEO is going on vacation the first week of January. It's 65% likely that the CFO is going on vacation in that same week. And it's 60% likely that they will both be on vacation that week. So if the CEO is gone, what's the probability that the CFO is also gone that week? In other words, we want the probability that the CFO is gone given the CEO is gone. So make sure you understand that notation. The thing to the right of the bar is given. So what's the probability that the CFO is gone given that the CEO is gone? Now we need to use this conditional probability rule. And so we have two events, right? The probability that the CFO is gone. That's B, right? CFO is gone. Event A, CEO is gone. And now we can just plug in the numbers. So, what's the probability that CFO and CEO are gone? That's the numerator. So let's focus on the numerator, right? The intersection. The probability that both are gone is 0.6. That's our numerator. The denominator is the probability that just the CEO is gone, 0.8. So the probability of B given A is 0.75. The probability that the CEO is gone, rather that the CFO is gone, given that the CEO is gone, is 0.75. All right, let's do another example. Let's look at the probability of red given even on our roulette wheel. So we want the probability of red given that it lands on even. So understand what we're saying. Look, we are saying it's given that it lands on even. Given this, what's the probability of landing on red, given that we've landed on even? And we agree that these are related events, right? So knowing if it's even changes the probability of red. Now, it turns out on this wheel, we already understand there are 18 red spaces. There are 10 odd spaces that are red, and there are 8 even spaces that are red. I didn't realize it's not 9 and 9. So guys, if you're going to go gamble, know that. So we need to employ our equation. We're going to use that conditional probability rule. So we understand this as the probability of B given A, which we can translate into the probability of red given even. On the numerator, we have the intersection, and on the denominator, we just have the probability of the given part, which is even. So the numerator is the joint probability, but these are not independent events, so we don't really have an equation that we can plug in there yet because we're about to cover that, but we can calculate this pretty easily by adding it up. So what is the probability of red and even? Well, I can go to my roulette wheel and see that there are 8 red and even spaces out of a sample space of 38, so 0.21. So that's my numerator. And the probability of the given part that it's even, well, there are 18 out of 38 even outcomes, which is a probability of 0.474. So all I have to do here is plug into that equation the numerator 0.21, that's my intersection, divided by the probability of the given part, 0.474, and when I calculate this, I get a probability of 0.443. All right, so guys, conditional probabilities, not confusing, but there is something that is important for us to understand. If A and B are independent events, then that means one does not influence the other. So then let's think about this. If I wanted to know the probability of B given A, but they're independent of each other, it turns out that's just going to be the probability of B. In other words, the probability of B given A is just the probability of B. Now you might be thinking, wait, what? Why is that? Well, think about it, guys. These are independent events, which means the given A part is not relevant. They're independent. A and B don't have anything to do with each other, which means there's no conditional relationship here. If you're still confused, let me give you an example. What if we wanted to know the probability of snow today given that it's a work day, Monday, Tuesday, Wednesday, Thursday, Friday? Guys, are those two things related? Is the probability of snowing, given that it's a Monday, Tuesday, Wednesday, Thursday, or Friday, any different than just the probability of snowing? No, it's the same thing, right? Because the part about it's a work day is irrelevant. So it's like we can drop that part. The probability of snow today, given that it's a Monday, is the same thing as just saying what's the probability of snow today? Because it's a Monday does not matter. Now, let's go back to our equation and we can see this numerically. Now, all I'm going to do here is plug in what we already know in the numerator. And what do we know about the numerator, right? We've seen the numerator before because that was our multiplication rule. So I'm going to take multiplication rule for independent events, that equation number 5, and I'm just going to plug it in, right? And I've got it there, but I've separated it into yellow and blue so you can kind of follow me. So I've started with my conditional probability equation. I'm taking the yellow part and I'm just replacing it with the blue part. So all I'm doing is plugging in equation number 5 into the numerator. All right, well, those of you that are math savvy are probably already seeing your way to this. What do you notice? We've got probability of A on the numerator and on the denominator. So isn't that like a form of 1, like 5 over 5 or x over x? We know that I can cancel that, right? So let's go back to this equation, cancel out our form of 1, and do you agree that we are left with simply probability of B? So if we have independent events where A has nothing to do with B, when I calculate the probability of B given A, the given part does not matter. It's irrelevant. It's just the probability of B. All right. Finally, we're done with conditional probability, and now we need to go to our multiplication rule for dependent events. Now remember, guys, we've already done it, number 5, for independent events. All we're doing is doing it for dependent events. And by the way, folks, this is our last probability equation. Woohoo! So we are almost there. So let's say in example 1 that we're going to draw a first and then a second card from a deck, but we are drawing with no replacement. Remember why I'm telling you no replacement? If we're drawing without replacement, then I'm creating dependent events. So we want the probability that both draws are red, that I draw a red and then a red. So we're back to this idea that we're calculating a joint probability, right? That something and something, the probability of A and B, in this case of red and red. So just like in the multiplicative rule number 5, but we have to change it a little bit. Again, in rule number 5, we had independent events. Are these independent events without replacement? No. If I'm not replacing the card each time, I'm creating dependent events. So the answer is no. That's why we're looking at this new rule number 7. Everyone understand that once we draw the first card, it's going to tell you more about the probability for the second card. For example, if my first card is red, do you agree it changes the probability that the second one is red, right? Now on the second draw, there's 25 red ones left out of 51 cards. The probabilities have changed. So I can't use the multiplication equation above from number 5. I need a new one for dependent events. Okay, I've beat that horse to death. So I think you understand where we're going here. The multiplication rule changes just slightly, but here's the thing, guys. It's not really a new rule. It's just a slight alteration. It's pretty much the same thing as 5 with an alteration. The rule here for dependent events is that the probability of A intersection B, of A and B, is the probability of A multiplied by the probability of B given A. That part in yellow has changed just slightly. So I need to look at the probability of B given A's happened because of the dependency. So when you draw colored marbles out of a hat without replacement, right, you understand. If half are blue and half are yellow, when I draw a blue one first, it changes the probability of the second one. That's why I have that yellow part. Probability of B given A. The probability of yellow given I already drew a blue. That dependence changes the equation just slightly. Now, I want to convince you, we haven't made much change. So let's go back and remind ourselves what the equation was. The equation was, for number 5, probability of A multiplied by the probability of B. Now, it's probability of A multiplied by the probability of B given A. That's the only thing we've changed. So compare that for a second. Look at these yellow parts. That's the only thing we've changed. So why was this part in yellow not in equation 5, that B given A? How come they're different? Well, remember before we had independent events. And when you have independent events, there's no relationship. B and A have nothing to do with each other. So it's just probability of B. Even if I wrote probability of B given A, it would still just be probability of B. All right, so let's use this multiplication rule. Let's say that we remove 2 cards from a deck, one after the other without replacement. We understand why I'm saying without replacement, because now I've created dependent events. We want to know what is the probability that the first card is the ace of spades and the second is a heart. So I have 2 events, right? A is ace of spades, B is heart. All right, so I have 2 different events, and do we agree they are not independent? The probability of getting an ace of spades, I can figure that out, but the probability of a heart when I've already drawn the ace of spades, that's going to impact the probability. All right, so let's work through the math. Let's look at our equation. We need to look at the probability of A and B, ace of spades, and then a heart, and that's going to simply be the probability of A multiplied by the probability of B given A, the probability of getting a heart, given that we drew the ace of spades to begin with. Now, the probability of A is easy. What's the probability of drawing the ace of spades? Well, the ace of spades is just 1 card out of 52. 1 card out of 52 has a probability of 0.0192. So there's now 51 cards left and 13 are hearts. That's the dependency part. We no longer have 52 cards. The probabilities are related. We have 13 hearts left. The probabilities are related. So we need to know the probability of B given A. So what's the probability of B given that we drew the ace of spades? Well, there are 13 hearts left and 51 cards, which gives us a probability of 0.255. So now when I put it all together, my probability of event A and B is going to be 0.0192, the probability of A, multiplied by the conditional probability, 0.255. And when I calculate that, the probability of this combination, I draw the ace of spades and then the second is a heart, is 0.0049. Now guys, remember, why did we need to look at equation number 6, the conditional probability first? Because we just used a conditional probability as part of equation 7, right? That yellow part is a conditional probability. All right. Phew, that's a lot, right? Before we wrap up, folks, we need to revisit this idea of independence versus disjoint. We've referred to independence, and we've referred to this idea of disjoint versus non-disjoint events, right? Outcomes. And we said that you have to know this. These are relevant in knowing which equation can be applied. And these are often confused because technically they're not the same thing. So let's just review these ideas one more time before continuing. So independent versus dependent, disjoint versus non-disjoint. All right, so if we're talking about disjoint events, we're talking about events that never occur at the same time. Those outcomes are mutually exclusive. There's no overlap. So we used examples of red and black in roulette. Those are completely exclusive outcomes, right? There's no overlap. But there's also other examples from the real world, and I want to throw these out here so that if you see an example, you can say, oh wait, disjoint or not disjoint. So classification in college, each student is either a freshman or a sophomore or a junior or a senior. There is no overlap. Nobody is in two categories. If we were talking about the sex of penguins, they are either male or female. If we're looking at a single coin flip, it's either heads or tails. If we're looking at something having to do with athletics, you either win or you lose a game, and those are mutually exclusive outcomes. But independence, we're talking about unrelated events. So disjoint, we're talking about kind of outcomes. Independence, we're talking about events where the outcome of one does not impact the outcome of the other. One event is unrelated to the other event. So our example has been first spin versus second spin in roulette, right? So everyone agree that what happens in the first spin has no impact on what happens in the second spin. But other examples, if we flip a coin multiple times, those are independent events. If we draw 3 names out of a hat with replacement, do you agree? Those are independent events because of the with replacement. If I look at the chance of light rain in relation to the chance that I go to work, those for me are independent events. One does not affect the other. Going to work doesn't affect rain, and having light rain does not change the probability that I go to work. So disjoint and independence, remember, we need to understand these ideas. Now we need to identify these cases, remember, because it tells us which equation we use. We've got 7 equations, right? Now, remember, disjoint or not, that was for the additive rule, right? When we look at the case of or. Independent or not, that was for the multiplicative rule, the case of and. And remember, we had 2 versions of each of these equations. So we really only have 5 equations where 2 of them have 2 different cases. So the additive rule we looked at, if it was disjoint, it was a little bit easier equation. It was equation number 2 on the left, right? But if it wasn't disjoint, it gave us equation number 4. Look at those 2 equations and remember, what's the difference between equation 2 and equation 4? The blue part on the right. That was the overlap that we had to remove. On the left for equation 2, there was no overlap, so we didn't have to remove anything. But in equation 4, where our Venn diagrams overlapped, right, probability of A overlapped probability of B, we had to remove the double counting. But gang, these are the same equation basically. So keep this simple. Then we did the same kind of thing for the multiplication rule. On the left, we had independent events, right? On the right, we had not independent events. Look at those 2 equations. They are the same except for the blue part on the right. On the blue part, we had to use a conditional probability because B and A were related events. They're not independent. But on the left, we just have probability of B because A does not have any influence. They're independent events. So aren't these the same equation with just one small refinement? So keep in mind, are these different? No, they really are not. The only difference, compare the blue to the blue, is that when you have independence, the probability of B given A is simply the probability of B because A is irrelevant, right? The probability of me going to work in relation to light rain, they're not related events. So the probability of me going to work is simply the probability of me going to work. These are not any different. And so I'm throwing that out there to help you understand how to organize this in your brain. Lastly, I leave you with a table again that you might want to consider printing and having in front of you as you work through problems. I think this will help you, but keep in mind that equations 2 and 4 are related and equation 5 and 7 are related. All right, so let's wrap this up. We now have all of the probability rules, people, and I don't disagree. This is a little confusing stuff, right? I haven't used probability for quite a while. We use certain things in economics, but we don't use all of this all of the time. So, this was a big review for me, and I am very conscious of the fact that for some of you, this is a little challenging. So I want to remind you that the trick is figuring out which equation to use and when to use it. And so you've got to ask yourself the questions: disjoint, not disjoint, independent, not independent. In the next video, we're going to practice with some more calculations. And as I said, I would refer back to the chart in the previous slide. I urge you to print it out and have it in front of you. I think that will be extremely helpful as you move on to the next lecture. And of course, as you do any type of questions for homework. So let me know if you have any questions at all, guys. And I appreciate you hanging in there. I know this is tough content, but we will get through this. Thanks for listening. Have a fantastic day.